Good morning, everybody. Today we're going to be starting motion in 2 dimensions. Now, that means the object is traveling along a curved path, not a straight line. Straight line is linear or one-dimensional motion. 2 dimensions, you're along a curve. Now, there are 2 types of 2-dimensional motions that we'll be studying this year. The first that we're going to be starting today is projectile motion. Later on, we'll take a look at uniform circular motion, objects moving in a circular path. Today, we're going to start projectile motion. Now, projectile motion is the motion of an object that is projected into the air. Now, how can we project objects? Well, we can toss them. We can launch them. They can roll off of an object like a ball rolling off a table. There are many ways to project an object. A golf ball is projected when hit with the club traveling down the fairway. A cannonball launched is a projectile. An arrow shot from a bow is a projectile. A bullet shot from a gun is a projectile. Even when a pitcher throwing a baseball, that is a projectile also. So there are many ways to project objects. One thing we have to understand about projectile motion is once the object is projected, it is in free fall the entire time. It doesn't matter if it also goes up as well as down. It is still in free fall because the only force acting on the projectile is gravity, assuming we neglect any air resistance, which at this level we do because we do not yet have the math background to deal with air resistance. It's a lot tougher. So we typically, for projectiles, neglect air resistance. So the only force acting on a projectile once it's projected is gravity. That means it's going to be in free fall. You need to understand that. Now, the projectile is the object that is projected, and it can be obviously anything. The trajectory is the direction of the initial motion of the projectile. In fact, that's what we would call the angle theta relative to the horizontal at which it's projected. The shape of the path a projectile follows is a parabola, and I've got some videos for you to watch that shows that. Now, one thing we need to talk about that pertains to projectile motion is an idea that is true through all of physics, but we usually introduce it right here in projectile motion because this is where we first come across it in the material. And that is the idea of frame of reference. Frame of reference. Frame of reference is just a fancy term for the viewpoint of the observer of an event. Now, I'm going to draw a diagram here. And once I'm done, if you want to pause and copy it yourself, you can. But let's suppose that we're standing on the shore and we can see out in the water a boat, like a sailboat. Okay? They want to make a sailboat. There's the mast. Only I'm not going to make the sails because they block our view of what we want to see. This particular boat has a crow's nest on the top of the mast. Y'all should know what a crow's nest is. That's the little sort of a basket thing near the top of the mast, and they send somebody up to stand in there with their spyglass and see if they can see land in the distance. Okay, so we've got a little person. Maybe that's a little too high up. He's not floating above it. He should be in it. Okay, so he is, there we go. He's in the crow's nest, and he's holding a ball. That little dot represents the ball. Okay? Now, what we need to understand is that this boat is traveling across the water at some constant horizontal velocity. Some constant horizontal velocity. Okay? So at some point in time, the boat will be over here. All right, here's the mast again, and the crow's nest, and a little person. Okay? So he's traveling from this point to this point across the water at horizontal velocity. Now think about this a moment. The person in the crow's nest stays in the crow's nest, so he is also traveling across the water at constant velocity. The ball he's holding in his hand is also traveling across the water at constant velocity. Okay, I'm going to call this person A. All right, this is person A. And over here on the shore is person B. Okay, doesn't have to be perfect. All right, so here's person B standing here on the shore. Maybe waving at person A, hey! All right. Now this is person B. Now, what does person B have to do with it? Well, person B is observing the ball that person A is holding. Now, here's what's going to happen. As the boat travels horizontally along with the person and the ball, person A is going to drop the ball so that it's in free fall. So, obviously, it will start from rest and accelerate downward. But here's the catch. The motion of the ball, the initial horizontal motion of the ball, doesn't just vanish because the ball is also now moving vertically. So that means the ball has an increasing vertical motion and a constant horizontal motion at the same time. That means person B on the shore will see the ball travel a curved path to the deck below. Okay? Why curved? Why not a straight line? Well, that's because, again, one motion continues constant. The other is increasing. So as the vertical velocity vector here gets bigger and bigger and bigger and bigger, it changes the direction of the resultant made by both. So we have constant velocity here, constant, constant, constant. So the resultant made by the two gets larger and larger and larger, and you get a curve instead of a straight line. That's kind of freaky, isn't it? Now, here's what frame of reference has to do with it. Person B on the shore sees the curved path the ball follows because he can see both the horizontal motion and the vertical motion added together. But what if we talk about person A's point of view right here? Remember, person A has the same horizontal motion as the boat and the ball. So when person A lets go of the ball, he doesn't see the horizontal motion of the ball at all because he has the same horizontal motion. He only sees the vertical motion of the ball. So for person A, the ball appears to just go straight down to the deck below. He doesn't notice that it's also moving forward simply because he is also moving forward with it. So person A is in the same frame of reference as the ball. He has the same horizontal motion, so he's in the same frame of reference. So the only motion he sees is the vertical downward acceleration. But person B, being outside the frame of reference of the ball and the person, sees both motions added together. So frame of reference, the viewpoint of the observer of the event. Two different observers because they each have a different frame of reference. Now, which frame of reference do we wish to look at projectiles? Well, we wish to look at the projectile from observer B's point of view. We want to see both the horizontal and the vertical motions added together so that we see the curved path. We want to be outside the frame of reference of the projectile, okay? Now, let's talk about another extremely important topic, and I'm going to do it in red because it's that important. And this is the idea of independence of perpendicular vectors. The independence of perpendicular vectors. This idea, this principle, basically says that perpendicular vectors do not affect each other in this motion, okay? If the horizontal velocity were to suddenly increase, maybe the boat goes faster, all right, the vertical motion will not be affected. The vertical motion also does not affect the horizontal motion. Gravity doesn't affect how fast the ball moves across the water. Okay, that's the velocity of the boat that affects that initially. So these two vectors are independent of each other at every point. The only thing they can change is the resultant they create when you add them together, which is why when the vertical component changes, then the resultant changes, all right? But the two do not affect each other at all. Now, let's take a look at the types of projectile motion problems that we're going to be dealing with. There are three ways to look at projectile motion, and we're going to start with the simplest. First is half parabola projectile motion. That means an object only travels half the parabola. You all know what a parabola looks like. So in this case, suppose you have a ball that rolls off the edge of the table. It has a horizontal initial velocity, and when it rolls off the table, it will begin to accelerate down. So it will travel half a parabola from the top down. Then we'll kick it up a notch, and we will look at full symmetrical parabolas, an object that's projected from the ground like a golf ball or maybe a football at kickoff, all right, and it lands on the ground down along the horizontal ground right there. It lands and creates a full symmetrical parabola, okay? Then what happens if you have something that does this? It starts on the ground, but maybe it doesn't get all the way back down. Maybe it lands on top of something, okay? So it reached the top and started down, but couldn't get all the way back down. This is what we call a non-symmetrical parabola, and it could go this way. You could end above where you started, but you could also end up below where you started. Let's say it was projected upward and then came back down and ended up below where it started from the top point. So you've got both the up and the down side too, but they're not symmetrical halves. This has symmetrical halves, this does not. So we're going to be looking at all three cases. All right? Now, I think that is, I'm not going to go any further right now because there are some videos I want you to watch first before we actually get into the half parabolas, and we'll talk later. Thanks, guys. Bye-bye.